You have stuff for me to your left. No, because it's actually, I always end up tripping over stuff over here. Yes. In this class, I tend to think of Newton in strictly calculus terms, but really Newton was a general scientist, a physicist, optics, philosophy in general. More commonly, Newton's three laws of motion. What's the second one? There are three. Let's just go through them all. What are they? That's related, but it's not exactly what this particular law says. And that phrasing is not correct for any of them, unfortunately. But there are two that are directly related to the way in which we describe forces in motion. Colin. Yes. So the second law is that force is equal to mass times acceleration. The first law, an object in motion stays in motion, an object at rest stays at rest, unless acted on by an outside force, the law of inertia. And the third one, for every action there is an equal and opposite reaction. But the second law says that force is equal to mass times acceleration. Hang on a second. Acceleration is a derivative. Now, depending on our units, we have to decide what we're measuring in. What is the unit for force? Newtons. Gee, what a surprise. All right. But if I'm measuring in newtons, what's a newton? Right. Kilograms, meters per second squared. But I don't live in an intelligent country. I measure in feet and inches, not meters. I measure weight in pounds. In this stupid imperial system, what do I measure force in? Say again? What's force in the imperial system? You're already measuring it. You think of pound as a weight, right? That's not a mass. An object whose mass is a kilogram does exert a different amount of force on the ground. An object whose weight is 1 pound is already measuring that force pushing down on a scale. The problem is, in the imperial system, we never thought of a unit of mass separately from a unit of weight. Technically, I need mass times acceleration. And acceleration in this system is feet per second squared. So a unit of mass is called a slug. Because literally they used a slug of lead to measure it. You will never, ever see that unit used ever again until you get to really complicated physics equations involving feet and inches. What that means is that when I say this weighs 100 pounds, its mass isn't 100. You measure weight by standing on a scale and pushing down, compressing a spring or compressing the electronic equivalent to get a measure of weight. That is not a measure of mass. In order to get mass out, when you get on a scale that measures your weight in kilograms, they're dividing by gravity. If I want slugs, I have to divide by 32. 32 feet per second squared. But what that means is if I go to lift a 20-pound weight, I know the force it's pulling down with is 20 pounds. Colin, I think you started to say pounds per something, right? I'm lifting. If I think of how much weight or force I'm exerting on an area, that's pounds per square inch, that's pressure. In the metric system, newtons per square meter is pascals. I hate the idea of naming all this after people. Name it after the units. That makes more sense. So, I have an object. I move it. There is a force that does not want me to move this up. The force of gravity wants it to go that way. I don't want to drop this. It'll make a loud noise in the classroom underneath me. But if I do that, I've put energy into the system, right? Measure energy in. Joules, calories, some British thermal units. I don't care. There's a measurement for energy, right? But I used energy to do this. .6 kilograms moved 70 centimeters. What's the work done? The work done by me to move the book. What's the work done? 1.6 kilograms, 70 centimeters. That's not a rhetorical question. But I need the right units for this, right? 1.6 kilograms, 70 centimeters. What's the work I'm doing? Okay, first of all, what force am I working against? I need the force in there to actually know what I'm working on, right? So I'm using force of gravity, 1.6 times 9.8. There's my force times my distance. Get the right units. Why'd I switch? I got to be in meters to be consistent with gravity. And I get Newton meters. There isn't a nice, simpler unit. I'm happy about that. I'm already unpleasantly worried about newtons being a compound unit. Newton meters. What would be the equivalent setup in non-metric imperial units? What would be the right unit base to do this? Well, not per, because I'm not dividing there. I'm multiplying. Instead of pounds per foot, it's pounds times foot, or foot pounds. Of course, that question. My handwriting sucks, I understand. You will often see, you will often see that unit more associated with torque than with work, but that's a force applied at a distance. So we're still multiplying force and distance together. So Newton meters and foot pounds are also often used for torque measurements, which is still an application of work done. Yes. Kilograms is always mass. The units itself. Kilos is automatically mass. I know we use it to think of weight, but it's not. Really, if I say I weigh 100 kilograms, I'm saying I mass 100 kilograms, and under the influence of gravity, I exert the same force downward as a mass of 100 kilograms. We just don't use a weighted idea of newtons in everyday behavior. But I really don't think you're going to tell me you weigh 9,800 newtons and have that make sense to people. People intuitively understand a mass of a kilogram and what that weighs. If I say, oh, this is 98 newton or 9.8 newtons, what? But that's definitely the physics pedant's problem. Other questions? Yes, ma'am. Right.
Like which one are you looking at to make sure what they're doing?
Ah, what are the units for gravity? So if I'm in meters per second squared, I should be in meters as well. We have dealt with meters as the base unit for almost every metric measurement. Kilograms and meters are more common. We used to deal primarily with centimeters and grams. So we use the KMS system when we think metrically. Kilograms, meters, and seconds are our base units. We used to use CGS, centimeter, gram, second. There are a whole different set of units for that. I was in McKenna this morning. I saw this happening. Although a 6-foot lift is a clean and jerk instead, right? How much work is done? There is no need to multiply by gravity this time because pounds is already in weight. That is a force, so it's just 20 times 6, 120 foot-pounds. You'll notice there's no mention of speed in here. Whether I do this slowly or quickly doesn't change the amount of work done. It changes the rate at which that work was done, but that's a different story. That's power. Whole different measurement. Both of these assume I'm working against gravity. Gravity doesn't change that much when I am here on the surface of the Earth. If I want to worry about gravity changing, I got to worry about much larger distances. So if my force is a constant, this is easy. If I were really going to look at moving an object against gravity, I might consider trying to launch something to outer space. Well, the further away from an object I get, the less effect its gravity has on me. Gravity is inversely proportional to the square of the distance between objects. So the further away I get, the less the Earth pulls on me. But I have to get quite a bit farther away for it to matter. So if I only move a little bit, my force is effectively constant there, right? And then I can just multiply. So if I took a little distance, there would be a very small change in the amount of force. I could say, okay, we'll pick some number in that distance, say this is the value of the force here. Then I move over a block. And I pick a number, and that's the measure of the force here. I keep moving. And as I get further and further away from the Earth, the force gets smaller and smaller. But in this little motion of, I don't know, a meter, the force is effectively constant. Maybe I've gone from it being 9.8 to being 9.2 or 7.1 or even 3. I got to get pretty far away for this to happen. But what I could do is I could take each little motion and I could say there'll be a little bit, there'll be some force if this is my x-axis. There'll be some value for the force in here. And I only moved a little bit. What's a little bit in calculus terms? delta x. A little bit, a little change in x. And work is force times distance. So I'll just multiply those, right? And then I add them all up. So I would take F times delta X, and I would add them all up. And I do it from the first one to the last one, right? So I would say, oh, well, we'll make this a spot. We'll make this the ith spot. And then we'll make it I going from, oh, wait a minute. I've seen this before. What's that look like? My buddy Riemann. Which really means an integral. If I want to deal with a varying force, I integrate. So, yes. So I said gravity behaves like an inverse square. The further away, the larger the distance, it decreases by the square of that distance. Well, a lot of forces behave that way. The power, the illumination of light is inverse square. Electric forces are inverse square. Magnetic forces are inverse square. With the exception of the constants involved, which is specific to the situation, what charge is on each particle, what magnetic force is on each particle, magnetic charge is on each particle, the mass of each object in my gravitational system, I can really say that for all of those inverse square forces, F is some number over x squared. When you're dealing with gravity, you need the gravitational constant. You need the mass of each object. When you are dealing with magnetic behavior, you need the magnetic permittivity constant. When you're dealing with electric behavior, you need Coulomb's charge constant. You need the amount of charge on each particle. But it's still, you're going to get some number on the top. If I think of a repelling force pushing my object away, and it's got that inverse square property to it, and we start 1 foot away and we end up 4 feet away, how much work was done? Yes, from x equals 1 foot to x equals 4 feet. I don't know K. I'm not going to bother figuring out what K is at this point. If this is an electron, then I need the electric constant in feet. Oh dear, I don't know that. If this is gravity, I need to convert. Okay, wait a minute, 32 feet. I need masses to do this right for gravitational behavior. And gravity is an attracting force, not a repelling force. Be work done against gravity. But I left the K there for a reason, because whatever that number is, it's just a number. I'll worry about it later. As a matter of fact, a large number of physics textbooks go back through and rewrite all the equations, making an assumption that gravity is 1. Because I can just multiply or divide by 9.8 wherever the hell I need to. So there's no reason to include it in all the calculations. There's a whole set of physics books that assume that just for the ease of making the calculations nicer, the speed of light is 1, as opposed to 3 times 10 to the 8th meters per second. I don't need that. It's just a number. I'll worry about it later. Call it C and just take it out front. So I'm moving from 1 foot to 4 foot. I'm dealing with this function. And I'm moving in x. So this is the integral I want to do. But K is a constant. So I'll pull it out front and leave it there. I pull the K out front, I have 1 over x squared. Let's rewrite that before we do anything with it. Now I do the integral. Antiderivative of x to the negative 2. Say again? Right. Really, it's negative x to the negative 1. We just do the simplification here. But I'm evaluating that from 1 to 4, so I don't need to worry about a plus c. K times put in 4, put in 1. Well, negative 1/4 plus 1 is 3/4, whatever K is. Units for that number. Foot-pounds. Sometimes it is easier to picture what we are doing as a Riemann sum first, and then worry about how to turn it into an integral. Hmm. Cable hanging off the side of the roof of the building. 100 foot of cable, 200 pounds. Haul it up. Haul it up to the roof. Hmm. The work is being done by me. I'm in pounds, I don't have to worry about gravity. I'm in feet, all my units are correct, consistent within this problem. What force am I working against? Gravity, really, because I'm hauling the thing up, right? If I was worried about friction, I'd have to mention something about the edge of the building and some coefficient of friction, static versus dynamic. Too complicated for the moment. We'll leave that to the physics class. I promise it gets done there. I'll make believe I have some nice easy wheel. I'm just turning a crank and hauling it up like I'm rolling up a fire hose or something. I know. It's Christmas. Remember in Die Hard when he jumps off the roof with the hose? I have to haul the hose up afterwards. I know the building blew up in the movie. We're not talking about that. I'm working against gravity. So I think to myself, let's think about the distance the hose is going to move, right? This little bit of hose right here. How far has it got to move? Not if it's at the very top, it doesn't have to move at all, right? It's already on the roof. So this is going to be zero movement. This piece down here. That's at the other end. That's 100 feet. So that bit of cable's got to go a lot further than this bit of cable. So the thing that makes the difference is the distance my bit is moving, right? So let's pick a piece in the middle. Let's pick a piece of cable in the middle. Boop. There's my little slab of cable. How big is it? How thick do you want to make that slice? 2 feet? Okay. If this piece is 2 feet, then how much does it weigh? 2-foot section. Right. The whole cable is 200 pounds. It's 100 feet long. So each foot of cable is 2 pounds. So that must be a 4-pound section. I don't know where that is. So let's just assume that its distance is some X value. Somewhere in the middle of that 2 feet, we pick a spot and call it X. So how much work is going to be done to move that piece of cable up? £200 cable, 100 feet long. So each foot of cable, you just said the magic word. There you go. But I could say that's going to be 4x foot-pounds, right? But what if I just said, I don't know how long that piece is? What if we made it really a very small piece of cable? What if its length, instead of being 2 feet, was some little slice. What do we call little slices? Delta x. Then it weighs 2 pounds per foot times the number of feet in that slice. And the work done is force times distance. And then I have to add all those up, right? Wait a minute. Adding all these slices up means doing an integral. So my integral should be 2 times delta x times x. Wait a minute. I need bounds to do an integral. What are my lower and upper bounds here? 0 to 100. How many foot-pounds of work did I do? But notice, rather than figure the force being what's changing, it's the fact that all the distances are changing for each little 1 foot or slab of rope that I'm pulling up. Cable. Questions? Who's taken a physics course already? Any physics course? The most common example of work in a physics course is a spring. Whether I compress a spring or extend a spring, it exerts a force in the opposite direction, proportional to the amount it's been distended. So if I take this spring and I move it so that the bottom of the mass has moved some distance, then there is a force being exerted by the spring. On the other hand, if I compress the spring, go from this right picture back to the left picture, it would depend on where the spring is naturally. If it started out here and then moved to here, then the force would be pointed downwards. That's why I just wrote kx. You'll often see that with a minus sign in it. I'll just move the minus into the constant. Oh, wait a second. Each spring, depending on the material it is made out of, the tightness of the coil, or the bend in a leaf spring, or whatever spring action you're looking at, the materials themselves tell me what that constant is. So normally we measure it by physically taking the spring, attaching a known mass to it, and finding out how much it distends. We have to find K. And I know in the physics lab, they've got this lovely setup with a vertical stand with a meter stick strapped to it, with a pipe clamp and a spring held onto it, and then a rod set on it, and a mass set on that, and it just bounces there. There are at least two different ways to do this problem. One of them is almost trivial, but I want to do the actual math. I have a 25 Newton force holding this spring out to 30 centimeters from a rest state of 20 centimeters. So the distension, the displacement, is 10 centimeters. You can do this in meters, you can do this in centimeters. K is a constant. Your units determine the magnitude of it. So if I do this in centimeters, my distension is 10 centimeters. If I do it in meters, it's 0.1 meters. That's fine. You'll only differ by the number of decimal places in your answer. 25 Newton force, K times 0.1 meters means that K is 250. And now my units are, look carefully. I have newtons on this side, I have meters on this side, right? So in order for K to work out, this has to be newtons per meter. K itself is a number, but because I'm using it in a united calculation, it's got to have a unit associated to it. Spring constant is measured here in Newton meters. It could be measured in pounds per foot or newtons per centimeter. Okay, if I want to hold it to 25 centimeters, what's the force I need? Say again? Say 12.5? Yes. It's K times X. But I got to make sure the units are right here again. If I'm doing this in meters, 25 centimeters from 20, my displacement's 0.05 meters. And so, yes, I get 12.5 newtons. I could also say, hey, I'm going half the distance, I need half the force. Half of 25 is 12 and a half. But think about this spring. If I'm holding it without stretching it at all, there's no force acting, right? I start to stretch. What happens? It starts to pull back on it. But with less stress, there's less pullback. With more stretch, there's more pullback. How much work do I do going from 0 to 20? So from 0 to 5, from 20 to 25. That 12.5 newtons is just what's needed to hold it there. That's a static force. Now I'm asking about moving it. This is the difference between algebra and calculus. Things move, and the force changes as we move it. So how much work do I need to do? To what? To go from 20 to 25 centimeters. The force is changing as I move. This is an integral. It's the integral of the force across the distance we apply it. I am going from a distance of displacement stretch of 0 to a stretch of 0.05 meters. My force is Kx. And I'm looking at adding those up over the entire little integral. Interval. So I know how much force I need to exert. How much work did I do to get there? Oh, integral of 250x. I got to multiply by the 0.05 squared. Unit. Newton meters. Okay, again, work done isn't usually written Newton meters. We named it after a person again. What was I heard somebody say it? Newton meters is joules. After the person who wrote the book. That's what we end up with. There are several more examples of writing a force that is changing as a Riemann sum and then turning that into an integral in this section. There's one about pumping water out of a well. I don't know, anybody need a septic tank empty anytime soon? Same exact idea. I will see you all tomorrow. Have a wonderful rest of your day. If you came in late, come give me your homework.